the Dark Energy Survey, have produced evidence for evolving dark energy which is independent of all other galaxy surveys. Cosmology is in a little bit of a state right now. The celebrated concordance of the past few decades is not there anymore, at least not in the simplest models with the simplest interpretation of the data. Nobody knows where the dust will settle. Missed subtleties in the measurements, new physics, a bit of both. But when we see evidence like this, we need to scrutinize it from every angle. What might have gone wrong? What could explain this? Can we see it anywhere else? One of the interesting things you will hear about in today's talk is exactly that. Baryon acoustic oscillation measurements from the Dark Energy Survey that point in the same direction with the same type of tension as the very tantalizing recent results from the Dark Energy spectroscopic instrument. The added benefit is that they can combine this with their own supernova data, which is also covered in the talk. Today we're joined by Jesse Muir from the University of Cincinnati, Juan Mena-Fernández from LPSC in Grenoble, Maria Vincenzi from the University of Oxford, and Santi Avila from CMB in Madrid. They're all also members of the Dark Energy Survey. Welcome, everyone. Juan, do you want to start by telling us briefly about your paper?
Yeah, so basically what we've done is to, yeah, as you just said, is to combine the latest baryon acoustic oscillations and type 1a supernovae results from the Dark Energy Survey. So these are the latest DS results for these two cosmological probes. And we do this to study implications for expansion history models, for the expansion history of the universe. And well, we use these two probes because these are the two geometric probes that we study in the Dark Energy Survey.
So yeah, what new insights did you obtain when doing this?
So the main results is that when we combine them together, BAO and supernova with Planck CMB, we find a 3.2 sigma deviation from lambda CDM when we allow dark energy to vary with time. So in this WA W0 plane, as you can see in this figure. So we are a bit over this 3 sigma from the lambda CDM point, which is WA0 and W0 of -1.
Oh, I guess the most interesting thing that might immediately leap out to an outsider is that DESI are also seeing this, of course, but your BAO are now, I mean, how independent is this? Are you looking at the same galaxies, somewhat using the same analysis methodology? I suppose your analysis methodology is relatively different because they're spectroscopic and you're not, and I guess you'll get into all of this, but...
So we are using different BAO sample. Most of the area of the sky that we're using is different area, and then we are combining with the same. Well, one of the three datasets that DSC consider is our DES supernova one, and also, of course, we are combining with Planck. So part of the dataset is in common, but the BAO it's relatively independent. Okay.
Okay. And it is your supernova that they get the highest significance with. But as I'm sure you're about to emphasize, your supernova are arguably the most, well, that they are the most recent catalog and arguably the most robust one. Okay, is there anything that leapt out to you when you were doing the analysis that was particularly surprising?
So one thing that we found surprising is that when we started looking at the first cosmological results, looking at the chains, and we saw that it was really difficult to reconcile the data sets together in the simplest model like lambda CDM to start with. And even when we open up the space for a bit more complex models, WCDM or K lambda CDM, we still couldn't reconcile all the data sets together. So this was a bit hard to digest and it took us a while. And eventually what we realized is that it was only when we went to the W0WA CDM model that we were allowed to reconcile all this data together.
I guess the one thing that leaps out in my mind when you say that when you go to this level of the kind of Taylor expansion, everything's suddenly consistent. Why stop there, or is it more of just an Occam's razor thing that we've got enough parameters? Why add more?
So the W0 WA parameterization is, a pretty phenomenological parameterization. It's a Taylor expansion of the dark energy equation of state in terms of scale factor. And so, yeah, there is a challenge in translating, what this tells us in this parameter space to what it might tell us about, say, more physical models of dark energy. For this paper, our focus was on the more phenomenological models that are very well studied. And yeah, the question of why not add another parameter, I think the focus here was, we want to get things to be consistent with as few parameters as possible. So there's a bit of an Occam's razor factor there. But then, also going beyond this, that we want to focus on things we can constrain well and that are sort of topical for the community. But there's certainly potentially more insights to uncover going after this with, say, either more physical models or studying how it responds to different parameterizations or degrees of freedom.
As we were sort of mentioning a little bit earlier, the other group that have been measuring the BAO and finding this interesting evidence for evolving dark energy when combining with the supernova is DESI. You mentioned you're looking at different parts of the sky. Are you covering more or less the same redshift though, or and what is your redshift space? Not redshift space. What is your redshift range look like? Yes.
So in our case, for DES, we are covering the redshift between 0.6 and 1.2. And if we summarize that in a single point, this is this red point over here. And so DESI would also have measurements at lower redshift and higher redshift. So I think it's quite interesting that for us with only 1 point, or we can split this point in sub-points, but this is basically just 1 point, we are getting the same level of tension or similar or comparable level of tension as DESI is getting. Here we can also see why we want to combine supernova and BAO, because both of them tell us about the relation between distance and redshift and how this translates to the expansion history models.
But I think, our kind of two big headline takeaways beyond the substance of these cosmology results, which we'll be talking through, is, the DES survey complete data set has been in hand for a while. We've now done the cosmology analysis with the BA, the geometric distance probes that we can measure from the completed survey. So we're very proud of that as achieving some of the major goals of this collaboration and observational effort. And then sort of in the wider context of other results, obviously these W0 results have been a topic of a lot of interest and conversation. And it is pretty notable that, in context with the DESI cosmology results, you can completely swap out the BAO sample and still see something fairly similar.
Since this was recorded, the Dark Energy Survey has done a reanalysis of the Dark Energy Survey Year 5 supernova data, which they call DES-Dovecki. This doesn't affect the BAO, but does somewhat weaken the conclusions from the combined datasets. You can see Juan giving a short update of these results using DES-Dovecki right at the end of the video. Okay, great. Thanks for the quick intro into the exciting results. Let's now get deeper into the background. Why is this interesting? And
so to step out and think about big picture, the reason we're interested, or what we're using BAO and supernova here are because they are both distance measurements. So the type 1a supernova, up to some details that we'll hear a bit about from Maria later, are standardizable to effectively have the same intrinsic luminosity, so we can use their observed flux to infer their distance, or at least the relative distance between different supernova that we observe. BAO, baryon acoustic oscillation, is a feature in the statistical distribution of galaxies that's imprinted by sound waves in the early universe. It's a length scale corresponding to the sound horizon at the time of recombination, or really the drag epoch, which is, for overview purposes, effectively the same, though technically a bit different. And that gives you a feature in the distribution of galaxies that has a specific physical scale, and then we can use how big that appears in terms of angular scale on the sky to infer the distance to the samples of galaxies where we're observing that feature. So we've got standard candles, we've got standard rulers. These give us distances. distances are very interesting for cosmology because by measuring the relationship between distance and redshift, that's sensitive to the expansion history, and the expansion history of the universe is sensitive to the overall matter and energy contents of the universe. So notably dark energy, as we'll be getting into in more detail. Then we can, in terms of why now for these particular measurements, as we mentioned in the intro, these results are based on data collected as part of the Dark Energy Survey. DES was a 6-year observing effort that the data was taken between 2013 and 2019. And so these are the first cosmology results from the BAO and supernova from the completed full 6-year data set. And so DES as a survey really includes 2 surveys. There's a wide survey that covers about 1/8 of the total sky down to a magnitude of about 23.8, detecting hundreds of millions of galaxies, which can be used for lots of different science, in this case for BAO. And then there's also the supernova, where there's 10 fields marked with the little dots on this map in the slide, which are visited sort of on an approximately weekly cadence over the first 5 years of the survey to look for things that vary in time and lets us build up this supernova data set. And yeah, an important thing to note, to put this in context with, say, other results from DESI, is that DES is a imaging survey or a photometric survey. So rather than pointing an optical fiber at each galaxy and getting a spectra, what we have is how bright each object is in 5 color bands, and we can use those colors to infer redshifts or distances. So with these data, there are 4 main cosmology probes that we analyze in DES. So the 2 that we're talking about, focusing on in this talk, the Type 1a supernova and BAO features in the distribution of galaxies. These are particularly and specifically sensitive to expansion history, but we do want to highlight that the data set allows us to also probe cosmology through measures of structure growth with weak lensing, galaxy clustering, and galaxy cluster counts. And there's a whole bunch of other exciting science one can do with this data set, including Milky Way science, solar system science. But yeah, our focus here is on these expansion probes. And these results this is particularly interesting at this time in the history of cosmology, just given the context of science results that have come out approximately over the past year. So here we have a little bit of a timeline for sort of the emergence and study of this pull away from lambda CDM when we consider a dynamic dark energy model. And that timeline starts in January 2024, when the cosmology results were released for the DES supernova sample, which I think you've had talks on this channel about before, where there was about a 2 sigma preference away from lambda CDM when we combined supernova with, at that time, I believe it was BOSS BAO and the Planck CMB information. And in this plot we have as well, combined with galaxy clustering and weak lensing measurements. Then in February 2024, that's when the initial measurement of these full DES survey BAO results came out. While we didn't at that time translate that into inference on cosmology parameters, compared to what you would expect for the BAO distance measurement, given CMB constraints and the assumption of lambda CDM, we were finding the distance being about 2 sigma lower than you would expect given CMB and lambda CDM. And then April 2024 is when the DESI BAO results came out, and looking at combinations of DES supernova, but also other supernova samples, Planck CMB and DESI BAO, this offset from lambda CDM grew to about 3.5 to 4 sigma. And then, yeah, our results that we'll talk about shortly sort of follow up on this and look at this with DES BAO. And
I was going to say that the fact that DESI was the exciting new stage 4 experiment, I think, is maybe unfortunate for the Dark Energy Survey, because January does in fact come before April in a year, but everyone's kind of thinking of it as the DESI stuff.
Yeah, and I think a takeaway that we'll see here, and that I think our results support the idea, is that these results and this pull away from lambda CDM don't seem to necessarily depend on any one of these data sets specifically. So like you can swap out the BAO sample, you can swap out the supernova sample. There were also like results out from ACT CMB measurements that also suggest that things look pretty similar if you swap out the CMB sample. Yeah, I mean, so the general picture of why is we have distance probes, which let us test dark energy based on the expansion of the universe. We have this really exciting data set from DES that we're ready to do a final expansion history analysis with. And it is a particularly interesting question given some other results in the field that we are able to add commentary to.
All right, let's get into the details now. I guess we've got the two pieces, the BAO and the supernova. And let's start with the supernova. How does one measure supernova with DES and get the catalog that you end up using?
Yeah, so I will just give a very brief overview of this DES supernova sample. And here I put like a nice light curve, supernova light curve from DES in the 4 bands we kind of monitored our supernova fields, GRAZ. And as you can see, the quality of the data, the cadence of the data was really amazing. But to put that into context, I usually like to start from showing this redshift distribution, in particular in comparison with some of the latest kind of most important supernova cosmological analysis of the past 4 years, which are Pantheon Plus and Union 3, which I think people have become familiar with, especially after the DES analysis. And one thing I want to emphasize is that this supernova cosmological analysis were using compilations of different supernova surveys from the past 30 years of supernova cosmology. They both try to combine like very low redshift supernovae, and in the supernova context, low redshift is anything below redshift 0.1, and the highest redshift supernovae, which is the second band in this histogram, which are supernovae within redshift 0.1 and 1. DES kind of released a very small sample in 2019, and this was included in this compilation. But this very final sample that we released in January really revolutionized this picture and basically managed to push kind of the number of supernovae with one single survey, one single instrument, one very well kind of control system, managed to add roughly 1,600 more supernovae that cover the high redshift range of this redshift distribution. DES couldn't measure supernovae at the very low redshift, mainly because the telescope would saturate with very nearby bright supernovae, and didn't have the kind of area coverage to get those low redshift supernovae. So the DES supernova 5-year analysis still had to rely on external low redshift samples, which here are presented in orange. And for those, there is a lot of overlap still with Pantheon Plus and Union 3. We tried to select the very best low redshift supernovae, the most recent ones, like in terms of release. This is our so-called Hubble diagram. So distance on the y-axis and redshift on the x-axis. And as Jesse was saying, distance versus redshift is where all the cosmological information is encoded. And as you can see, one of the characteristic of the DES supernova sample, and also one of the reasons why DES could collect so many more supernovae and go so much deeper, is that for each of DES supernovae, we didn't require additional external spectroscopic information that confirm that the supernova is effectively a type 1a and not a core collapse. We decided not to do that because that presents an extremely narrow bottleneck in terms of the data you can use. So what we did is we take advantage of the very high quality of the light curves of DES and use the shape of the light curve, so the photometry, to classify whether a supernova was a type 1a or not. We heavily relied on machine learning and to kind of, from the shape of these light curves, determine the probability of each event of being a type 1a supernova. One of the things we spend most time doing throughout the analysis was looking into the systematics that might affect our measurement. First of all, what I just mentioned, contamination from events that are not supernovae 1a and that might have been misclassified as supernovae 1a. And there are a lot of paper and a lot of detailed analysis that really stress test our machine learning classifiers, supernova classifiers, and really check that their performances are adequate for high precision cosmology. But then here I try to summarize, even if it's very difficult, all the different analyses that kind of checked one by one each systematic that could affect our measurement, from calibration, modeling of the light curve, association of the supernova with the correct host. And it was really a team effort in trying to quantify, make sure we had a very good understanding of how each of the systematics can affect our final cosmological results.
It might be worth mentioning at this point that you and Tamara and Dylan being two other people in this army of people that you've got at the bottom, did have a talk on Cosmology Talks last year, where I think you went into maybe not every single one of these systematics, but you went into a lot more detail how you tried to test all of this stuff.
A way to visualize how the systematics affect our measurement. Here I present a sort of error budget for, in this case, for the parameter W, assuming we're living in a flat WCDM universe. So if this is the statistical uncertainty you get purely from how many supernovae that could collect on the parameter W, if you consider all the systematic uncertainties, well, this uncertainty, the overall uncertainty on our W parameter increases by a third roughly. And if you check what are the systematics we're more kind of limited by, well, contamination from non-1A supernovae, which is one of the most kind of peculiar systematic of this sample, is actually one of the tiniest systematic uncertainties, while other systematics related to the astrophysics of supernovae 1A, how the variation of their intrinsic brightness, which we know being small but it's not zero, how this affects our cosmological measurements. Those are the limiting factors we will need to tackle for future experiments.
So this is for just W. So I assume in a model that is WCDM where WA has not been varied, but is it more or less the relative sizes are going to be exactly the same in the full W naught WA model?
In our papers, we have kind of a similar plot for like the W naught WA figure of merit, and the story doesn't change much. In a sense, one thing that I would mention is that these systematics are very peculiar of the supernova measurement itself. Of course, BAO and other probes we're combining here, supernova with, are completely insensitive to this probe, to these systematics. So that kind of the advantage of kind of doing this kind of combinations.
Cool. Okay. Let's now look at how you get the BAO. I think in particular, it's interesting that you can get BAO with photometric redshifts. For me, at least, it's clear how one does it with spectroscopic redshifts, because you have quite a precise distance measurement there once you've anchored it in some way or another. But with photometric redshifts, perhaps it's just as simple as if you have enough galaxies, you can shrink the statistical noise enough and it works that way. But yeah, let's get into the details of it.
So as you said, when building the sample that we use, the sample of galaxies that we use to measure the BAO in DS, since as you said, it's a photometric survey, we don't have access to the spectroscopic redshift of galaxies. So, however, on the other side, we have many more galaxies. For example, when you have a spectroscopic sample. So yeah, there's few factors that are entered there. First, for example, the width of the redshift bands when you build your sample, they cannot be like too wide, because if they are too wide, the biosignal will just disappear. And if they are too small, then you will not have enough galaxies to overcome cosmic variance. So you will not see your biosignal at all. So you need to have it's kind of a trade-off between these two things. And once you have that, if the quality of your photometric redshift is good enough, you will end up finding the biosignal there. Also, again, because we have a lot of galaxies.
Just a quick order of magnitude comparison here. So you've got 16 million photometric galaxies. What is it that was SDSS's last spectroscopic sample, and what is the current DESI sample size of their spectroscopic ones?
Just because I was involved in the EBOS analysis, particularly at the redshift range, very similar redshift range to the one we're using here, There was the ELGs from EVOS, and it was around 200,000 ELGs. And the total SDSS was 2 million. But just to remind you, 16 million galaxies is not all the galaxies we have, it's just a subsample that has good redshift. So you don't take all of the galaxies, but the one that will give you the best signal.
We run some forecasts to select those galaxies that will give us the best BAO measurement possible.
Presumably when you do the cosmic shear analyses, you leave in all the other galaxies because the redshift there is important, but not quite so utterly essential.
Yeah, the cosmic shear samples will have, well, for year 3, there were about 100 million galaxy shapes, and for year 6, that will step up for what is equivalent to twice as much data, so like 200 million.
But then the lens sample, it's like order of magnitude of this one, right? Like maybe 10 million galaxies, something like that.
Yeah. Yeah, so when we sub-select for galaxies that we can do a bit better on the photometric redshifts for BAO or for measuring galaxy clustering in a more broadband way, we cut from, hundreds of million down to tens of millions.
So our final BAO sample is divided in 6 tomographic bins, and it spans from redshift 0.6 to 1.2. And the effective redshift, it's around 0.85. So something that we do is we have 3 different estimators for the redshift distributions. It's important to be sure that we are estimating them correctly, and we have 3 different estimators that we combine to obtain our final redshift distributions that we use to compute these templates, because in the end, this BAO measurement, similarly to DESI, uses a template-based algorithm. We have 3 different clustering statistics, namely angular correlation function, its Fourier transform equivalent, the angular BAO spectrum, and also a projected correlation function that does not depend on angles, but rather depends on the comoving separation between galaxies across the line of sight. And I will show you some results later about this and talk a little bit more about it. Then we have we run lots of tests in over 2,000 simulations, almost 2,000 simulations, just basically because the analysis is performed blind, and to be sure not to unblind too soon, like not to to try to avoid confirmation bias, we do lots of tests before unblinding, and when we are sure that we can unblind, that everything's under control, systematics, and we don't have any problem, that's when we unblind, and that's why the simulations are very important in our analysis. So yeah, as I just mentioned, we use a template-based method. There on the right, you can see a plot showing our data, our angular. Well, this is the projected correlation function actually, as a function of S perpendicular, which is the comoving distance between galaxies, but across the line of sight. And you can see our data points with error bars, and you can see the orange dashed line is the Planck template, which is a theoretical projected correlation function computed for lambda CDM and assuming the cosmological parameters from Planck 2018. And basically what we do is when we measure the BAO, is to shift this template to fit our data. And the amount we shift is the alpha parameter that is shown there in the bottom left side of the slide. And in our case, this alpha parameter is just it's a ratio of the comoving angular diametric distance and the sun horizon scale, also divided by that same quantity evaluated at the cosmological parameters of the template. Again, the template in this case is Planck, and again the difference in the alpha is what the orange, the blue line moved with respect to the orange one.
I mean, am I just doing too much chi-squared by I here, or aren't your data points already some large number of sigma away from the Planck template here? So aren't you already measuring a cosmological parameter to be different? I mean, maybe this is exactly the point, that your measurement of the expansion history and Planck's measurement aren't consistent in lambda CDM, and I'm just jumping the gun a little bit.
Yeah, actually, I mean, the fact that our data points do not fit well to that Planck template is because our BAO measurement in the end is a little bit far away from Planck, like 2.1 sigma. So you have to move it a little bit, and in moving that's when you get away from Planck.
Okay, and then in like a final kind of cosmological parameters sense, it'll mean that your like omega matter measurement or omega lambda or something is slightly different to theirs within lambda CDM. I see. Okay. Yeah. Fair.
Yeah, well, actually, you can already see it on the equation for alpha. When you solve for dm over rd, that measurement is gonna be like alpha times away from the prediction from Planck.
You're right that here by I we already see this difference, and this is what we quote as 2 sigma. Actually, we don't use this specific data for our analysis. The one that we're showing, this is more for visualization. Because this one in particular, if I remember correctly, it was actually 3 sigma, but there was some systematic there that, so I think it's a bit of a word of caution that this will be more like 3 sigma, but this is not the one that goes into analysis because, it was less reliable than when we do beam by beam. So we are actually doing this, we are doing all the data sets together from 0.6 to 1.2. And the actual analysis, it's the signal is split and it's more robust, and that's the one that actually goes to analysis.
Okay, no, I think that is valuable because this does look like more than 2 sigma. But I mean, chi-squared by I, as always, things can look like 5 sigma.
Another word of caution is that the data points are highly correlated.
Sure.
Yeah, but that's a particularity of the Pareto correlation function, that you can plot a single correlation function for the entire sample, like from 0.6 to 1.2, instead of dividing redshift bins as we do for the angular correlation function, as I will show later.
So on this slide, you can see basically our data vectors. We have as I said before, we have 3 different estimators for the galaxy clustering. We have on the left the angular correlation function, which depends on the angular separation between galaxies projected on the sky. For the 6 tomographic bins from high redshift to lower redshift in the plot. Then on the right, you can see the angular power spectrum, which is the Fourier it says the Fourier transform of the angular correlation function. And in the bottom right, you can see the projected correlation function that depends on on this co-moving distance between galaxies across the line of sight. And something that I wanted to say here is that in the angular correlation function, since it's a function of an angle, you can see that if you go from blue to brown, you can see that the BAO feature is moving to lower angles as you increase redshift because of the constant moving size of the BAO scale. However, in the projected correlation function, in the plot on the right, you can see that the BAO feature is located at the same scale because it's a moving distance, moving scale, and it's located at around 100 megaparsec of H in every redshift bin. And then in the angular power spectrum, instead of a single BAO peak, you can see that a set of oscillations.
Can you just unpack a bit more what the projected correlation function is?
So it's kind of a 3D correlation function, but you integrate along the line of sight. So you only have the across the line of sight part. So you can think of the correlation function as a function of 2 distances, like along the line of sight and across the line of sight, and you just integrate along the line of sight because in DES, since we are a photometric survey, that information is not useful for us.
Okay, so that naively I'd have thought that was very highly, if not almost 100% correlated with the angular correlation.
So the correlation we estimated from MOX, and it's between 85 and 90%. But when combining the results, since the correlation is not exactly 100, we are still obtaining some information from the combination of the 3.
Okay, and related to that question, the angular power spectrum and angular correlation function, I'd have thought are mathematically 100% correlated. So what do you mean when you say you've got 3 different statistics? Surely they are the same statistic.
The methodology, yeah, exactly. But the methodology used to analyze them is different. Also, the scale cuts are not quite the same because you cannot map the scale cuts from configuration to Fourier space exactly. So those kinds of, also the way you measure the angular power spectrum, angular correlation function is completely different. So all those things make a little bit of a difference in the analysis. That's why when combining them, we get more information than just using one of them.
So given the high correlation, you don't get statistically a lot of it. You still get some, but also having different methods also could reduce your systematics if there was one systematic in one of the methods.
Yeah, naively I'd have thought you would then just quote 3 different values rather than combining them. But
we also quote them individually, but in the end we combine them because we gain a little bit of information, and then we can use just a single measurement when running our chains and our stuff. And the combined result is shown there, by the way, the bottom left. That's our alpha at redshift 0.85.
Where 1 would be what one gets from the Planck lambda CDM cosmology.
Lambda CDM. That's exactly right. So here we have the BAO angular distance ladder released in 2024, including our measurement as an orange star, and also the results from DESI for the different tracers that span all that redshift range, as you can see there. And the black line would be Planck, and you can see that our measurement is about 2 sigma below Planck. And yeah, just a little bit of a highlight of our main message that we sent in the paper is that we got 2.1% precision angular BAO measurement with a 3.5 sigma significance of the detection of the BAO peak. Our measurement is like 4.3% below Planck or 2.1 sigma, and is the most precise BAO measurement from a photometric survey, which is very nice.
Okay, we now know how you get the BAO and how you use the supernova to measure distances, and how do we combine these two?
Okay, so once we have these two ingredients, we now want to see what they tell us together about the expansion history models. Well, I remind you again that both of these probes give us constraints on the distance to resist relation, which basically is an integral of h of z, which basically tell us about the content of the universe, how much matter there is, well, the expansion history, the expansion rate today, whether we have any curvature in the universe, and about dark energy, how much dark energy we have, and then the type of dark energy that we have, right? So this has been a very interesting project, working with many people across the collaboration from different science working groups. So it was interesting to see also how different groups work together, like from the supernova side that were working on the supernovas, and then us working on the galaxy clustering, and then the people from the theory working group. I think it was very interesting to finally see all the collaboration together on this project. Then I'm going to start by summarizing which datasets we are going to be considering when joining cosmology results. So basically, we are considering our own BAO. We'll just call it BAO, and our own supernova set, so just supernova. And then we will be using Planck's CMB, temperature and polarization power spectra. We are not considering lensing because we want to leave a growth of structure aside from this analysis. And then in some cases, we will also check what happens if we don't consider full CMB, but just the angular scale of the acoustic peak of the CMB, this theta star. And we will also be considering at some point priors from the Big Bang nucleosynthesis by this reference.
Can I just clarify something? When you say you don't include the lensing in the CMB, does that mean you only don't include the like reconstructed lensing power spectrum? Because the small scale temperature anisotropies are still affected by lensing. Have you removed that in some way, or is that kind of still in there but just not as dominant?
Yeah, the impact of lensing on the CMB temperature and polarization power spectra are still there. We just mean by this we don't include like the 4-point lensing reconstruction map.
Okay, so if we start looking at the constraints in lambda CDM, supernova can constrain very well omega matter, preferring a high value of omega matter around 35. And on the other hand, BAO on its own, we only have one data point, so couldn't give you much of a constraint on its own. But if we combine it with BBN and theta star, then we get this competitive contour on the left. And here is where we find the first tension. No? We can see that these datasets are in some level of tension, which is somewhere between 2 or 3 sigma. But this is not the only one, so we're gonna keep looking at other combinations. And then on the top now we see this combination with this, which is BAO plus supernova plus BBN. And at the bottom we see BAO plus supernova plus theta star. So we see very hard to try to reconcile all of these measurements together.
Can I just understand, the BAO plus supernovae is in lambda CDM? Like you're combining I'm just wondering, like it seems like you're combining things that are clearly inconsistent.
like the combination of everything is not here, so there is always one missing in each of these. If you realize there are 4 things, so if we put the 4 things together, then we arrive to this purple curve, so which is in between the other 3.
But the green line that you was showing first is not just BAO, but it's BAO, BBN, and theta star. So the idea of trying other combinations is to see what is driving the fact that the green line is out of the green shaded band, right?
And then, of course, all of these are intentions, so you shouldn't trust what comes out of the combination of the 4 of them. But if you did, you could wonder where this lies, and it lies in this purple contour, which is very close to where the CMB contour is, which is in black. And then the other question we ask here is what happens if we add to the CMB BAO, and then this pushes to the left, so to lower omega mater and higher H naught. And supernova pushes in the opposite direction, so this would be going supernova plus CMB prefers a larger CMB and lower H naught. So the conclusions is here that, yeah, basically the data sets are intention. We cannot reconcile them together in this in this parameter space, and also that BAO and supernova are pushing in different directions. So then the question is, okay, then maybe let's try something beyond lambda CDM, and well, one natural extension is to just open curvature. And if you do this, actually the tensions are not resolved. Actually, you can't see some of the tensions are even stronger. So yeah, for example, one clear way to see this is this purple contour, which again is BAO plus supernova plus William plus theta star, so the combination of all the background probes. And then compared to the CMB, which has a strong degeneracy in this direction when we open curvature.
I don't think you ever explicitly said, although it has been mentioned on this channel a few times before, but what the BBN plus theta star is doing here. Do you want to just quickly unpack that in like a 30-second explanation?
The BAO, as Juan was mentioning, basically constrains the ratio of the angular distance at a given redshift to the acoustic scale RD. And this basically this acoustic scale depends on basically subbaryonic acoustic oscillation, right? So that occurs at the beginning of the universe. So it depends mostly on omega baryon. It also depends on omega mater and other cosmologies, but omega baryon is the main thing that you need to complement this. So BBN give us a constraint on a omega baryon H square, and theta star it also give us this same acoustic scale at the CMB epoch.
So then when we're looking at the BAO at more local redshifts, it's providing an anchor to the actual absolute distance that you're looking at.
Yeah, so basically this both of these quantities help us to calibrate the BAO so that then we can isolate the distance, the angular distance. It's a bit similar to what happens with supernova. No? You could potentially calibrate the absolute magnitude with Cepheids and so on to get the H naught. No? So this is a bit like.
And well, sorry, I may maybe dwell on this for a second, but the theta star is taken from the CMB. So maybe it's a little bit funny that you've got the kind of inconsistency with the CMB. But again, I guess your conclusion that, okay, things are fishy, one shouldn't read things off from this model is fine if you're doing it in this way and it's inconsistent, so long as you say, therefore it's inconsistent, so therefore not trustworthy. I guess that's all fine.
If you wonder what omega k values we are getting from this, is that basically depending on which combination you choose, you get completely different results. So you can go from very negative cases to very positive cases to things that are compatible with 0. I'm not going to go through all of this. I mean, you can have a look at the paper, but yeah, I mean, I don't think you need to take any. I think what this is telling us is that this is not working. No, that omega k could be anything depending on the data sets that you choose.
Yeah, it's not the correct model to explain what's happening. Neither was lambda CDM, but this is not either. Actually, just by the way, I like that you're presenting it this way, because it does show that W0 WA wasn't just like the first thing pulled out of a hat and like, hey, look, we've got evidence for it. It's like it, in some ways, it is actually, it's still an empirical model that is not kind of, there's no physical model that says it has to be cut off at this order of the Taylor expansion. However, it is a model that seems to reconcile everything. So if you're building the theory model, you do need to keep that in mind, that these other models, W and K, lambda CDM, don't work.
Well, yeah, this is how we presented it, but also how we found it, I think, because it was not that we were specifically, I mean, of course, we were interested on the W0 WA results, given what happened last year, but yeah, I think it took us a while to realize, oh, what's going on in lambda CDM? Oh, what's going on in K lambda CDM? Oh, what's going on in W CDM? And then eventually we arrived to W0 WA, and things were compatible. So then the other natural extension that we tried is WCDM with a free equation of state for the dark energy. And what we find here is that, again, the tensions among probes persist at a 2 or 3 sigma level. I think the most clear case here is the supernova in green that is around 2.5 sigma away from the combination of CMB and BAO in red. Well, in this case, even though these are coming from combinations in tension, if we wonder what is the most constraining case from our combination of BAO plus supernova plus CMB, we would have this W, which is around 3 sigma above -1 with a 3% precision. But of course, one needs to take this with a lot of caution because this is coming from datasets in tension. So what else can we learn from here? The thing again is that BAO and supernova are still pushing in different directions. And since they have different effective redshifts, this could be already a hint for an evolving dark energy. So that's what we will look at next.
Yeah, this is like it came naturally, like trying to interpret data in W0 WA, knowing that in the other models we didn't manage to reconcile our different observables. And in W0 WA we were able to. Here we're showing the constraints in W0 and WA. Of course, this is marginalized over all the other parameters, but actually even though you can see here that the different data sets are consistent in this particular plane, it's the case for the entire parameter space, which is the way we compute the tensions between data sets within a given model. So yeah, our main result again is the one that we showed at first, which is the orange contour, which is a combination of BAO supernovae and CMB. And yeah, as you can see, all the different probes the different data sets are consistent here. We also consider other data combinations, not just, even though the orange one is our like fiducial result. We also consider, for example, the combination of all the geometry probes, which are BAO supernovae, BBN, and theta star. And yeah, of course, the concerning power is worse because we're removing CMB and adding BBN and theta star. But we see that we still find quite a significant deviation from lambda CDM of 2.8 sigma, a little bit lower than the 3.2 that we find for the other one, but still, this is telling us that yeah, our data is preferring W not WA compared to lambda CDM. Then we also tried other things. For example, again, the same data set as before, but without any CMB information, removing theta star, but adding a prior on the edge of the universe, basically, because for combination of data sets that are not very constraining, they are not able to constrain the edge of the universe well. And adding a prior on the edge of the universe really helps when constraining cosmological parameters here. And this is the gray line that you can see, which is all the, again, all the background probes without any CMB information, plus adding the edge of the universe. And you can see that the results, even though the the constraining power is a little bit worse. It's still consistent with the other two contours shown here.
What is that prior? Is it like set by the like ages of the oldest observed galaxies, or?
Yeah, it's given by globular clusters.
Okay, so it's like a maximum or minimum. Well, yeah. What is it? A maximum or minimum age, or?
We consider both options in the end. So there was the option to only have a minimum age, but we are considering here, well, following on what they do in this paper, a Gaussian prior on the age of the universe. They assume some reasonable range of stellar formation models, and this gives you also like both a lower and upper limit. Of course, this has to be taken with caution, but I think it was an interesting addition to explore how these priors could help you to limit part of this parameter space.
Yeah, are we talking about 13 billion plus or minus 3 billion plus or minus 2 billion, 1 billion?
0.5.
Plus or minus 0.5. Okay, so it is quite a narrow age of the universe prior. I don't know enough about galaxies to know. I'll take your word that that's a fair prior. It feels very tight, but
I mean, in the text even below that, there was a value quoted for what the constraint from Planck is, and it's a similar center, but like an order of magnitude tighter constraints. Like, so it's a much weaker prior on that than like what you would get from using the full CMB information.
sure. But if you work on galaxies and you think that that's too tight, then rant about it in the comments.
And here in this slide, we also run a chain combining the CDR1 BAO plus supernovae plus CMB just to test consistency with the baseline DESI result. And we got our tension estimation is different from the one is using DESI, but the result is very similar. And here you can see the basically orange is with our BAO measurement, and the pink is with DESI DR1 BAO measurements, and you can see that, yeah, of course, our constraining power is worse, but the the deviation from lambda CDM is similar, a little bit bigger for the BAO, but it's consistent.
Why not combine the two BAOs and start getting above 4 and?
So in the paper, we do that. We show the combination, but we have to be careful because we don't take into account the correlation between the two. And since our galaxy BAO sample has a little bit of an overlap with the DESI footprint, even though most of our footprint is in the southern part of the South Galactic Cap, there is still a little bit of an overlap with the northern side of the South Galactic Cap, which is where DESI starts. That little bit of an overlap, we didn't take into account any correlation, but we show this result in the paper. So our BAO measurement moves a little bit the contour away from lambda CDM.
So you take their 3.6 sigma and turn it into a combined 4.2 sigma. But that was the year one. So I guess the DESI 2025 BAO, which is above 4, would then jump perhaps by a similar amount, or maybe not, because maybe they're now more constraining and therefore your extra power is not as much as it was compared to their first year.
That could be the case. We haven't tested that, but yeah, we should add this to our to-do list actually.
But at least in the story one tells about this, that their whatever 4 point whatever sigma now is still being backed up by the fact that your independent BAO measurement is also pointing in that direction. So
I think also something that is remarkable here is that, yeah, so this is only 1 point with one angular BAO point, and we are getting a similar level of tension as with DESI 7 points with both radial and angular BAO. Of course, this is maybe partially because we had already this 2 sigma deviation from Planck, but I think it's interesting.
can we, maybe dwell a bit more on the consistency here? Something funky looks like it is happening, but not so funky that maybe things are inconsistent. But by eye, because I can't see the omega matter axis here, of course, but by eye, one would have expected the combined green and red not to lie where the orange is. So there's something happening in that third axis that is actually preferring slightly higher. So they're not in like 2 sigma tension, but okay, 1 sigma tension is not a tension, but there is something happening where omega matter is forcing things higher, right? Am I reading this correctly? Because the green and red are most consistent in this 2-dimensional axis, much lower down. Because you have been showing on all of the other models the omega matter axis, which seems like the crucial one where things aren't consistent. So
yeah, so here you can see, for example, that CMB by itself is not constraining omega matter that well. And then also when combining CMB and our BA measurement, since our BA measurement is just a single point, it's not helping that much constraining omega matter.
But this does look like everything's consistent, and I think it's important to analyze this to see that even when you hone in on that W0 WA plot and see what, because that's the exciting one, it's the new physics, that you're not getting weird stuff happening in omega matter to do that.
Yeah, and maybe just to emphasize that in the course of this analysis, something that we haven't dwelt on in the slides, but it's part of the analysis, is we have a couple different, well, we make a point of assessing the tension metric based on parameter shifts in the higher dimensional parameter space, and report that for all the models for a number of different data sets. And so for, like, in a quantitative sense, in W0 WA, things agree all under 2 sigma. And yeah, maybe as just another point for interpreting the higher dimensional parameter space, something that can kind of guide the eye here is like the fact that the supernova tend to prefer a slightly higher omega matter in lambda CDM is manifesting of, like, in W0 WA, adding supernova to the constraints also pulls you to a higher omega matter, and W0 WA is giving you enough freedom to, like, capture that with the other measurements. So the pull from supernova towards higher omega matter will also pull you towards that quadrant of the W0 WA parameter space. So this sort of theme of the pull in different directions of omega matter carries through all of these models we look at, but it's in W0 WA where there's now enough freedom in the model that you can fit everything decently well.
Yeah, this is it is interesting that the W0 WA model does seem to work, even though it's not physically based on a model. It's pointing in the right direction. Whether that right direction is some sort of systematic effect that is affecting high and low redshifts differently, or a new physics, it's certainly pointing in the right direction. And I think you've shown that quite compellingly with the W and K CDM models not pointing in the right direction.
Of course, the complicated thing about W0 WA is the phantom crossing and all the things that implies, which can be complicated too.
Yeah, I mean, you're not the theorist, so I wasn't going to bother you about that. But if you have thoughts about that, I mean, give a theorist a problem and they'll model build their way out of it. There are certainly models that have been written in the last 12 months that claim to do that without issue.
Yeah, I believe that I don't know that much about it, but like some modified gravity models can deal with that, like with the phantom crossing without it being an issue. But just general relativity, it's not the case.
The other thing, of course, is that this doesn't necessarily have to be dark energy. What you're seeing is that the expansion history is changing, but I mean, as you can see from a lot of these plots, omega matter is playing a huge part in how things are looking, the amount of matter in the universe. So if that is also being changed by things stopping being matter and becoming radiation, or vice versa as they cool down, or whatever, that's another kind of player in this game of trying to work out what new fundamental physics might be causing this.
Yeah, that's right. And yeah, we're seeing in the expansion history the effect of the total energy density in the universe and how that affects the expansion history. And this is telling us that you need some time-dependent modification from what we get in lambda CDM. We're parameterizing this in terms of dark energy equation of state because we're particularly interested in dark energy, but one could potentially think of models where you maybe modify dark energy in some way or have some modification of matter density, or something else could be going on that affects expansion history in a way that requires 2 parameters that give you this freedom in redshift. But yeah, I don't think we have enough here to say that, like, this particular type of model, or it definitely being in the dark energy sector, is the only thing that would work. I think these last 2 points are just kind of brief other things we are able to look into.
Right. So this is actually a question that I've gotten a couple of times, like, is the Hubble tension solved by in W not WA CDM? And the answer is no. You can see here our constraints on H naught for, well, in orange for lambda CDM, then blue for K lambda CDM, and different colors for different models. And you can see that the results are quite consistent, and the gray area is the measurement of H naught from CMB alone, assuming lambda CDM, and every measurement shown in this plot is consistent with that. And the red region, the red region on top, that's the measurement by distance ladder. And you can see that the tension is there, and W not WA is not solving the tension, which would be like the purple points, the ones we obtained for W not WA. So yeah.
In some ways, this is maybe surprising because, and this is also related, I guess, to the fact that when you only look at the W model, you still are close-ish to -1. I mean, even if statistically significantly far away from it, in a percentage sense, you're close-ish to it. That whatever is happening, that it first goes below -1 and then goes above -1 to kind of cancel itself out, so that the expansion history at its final point is still looking more or less the same. Could be a coincidence, could be something else. I don't know. Yeah.
I feel like this, I don't know, this is kind of a coincidence in the same way as before when we were putting all these data sets that were in tension, and then when we put them all together, they go like to the CMB value. It's a bit like that.
I mean, the other thing is that this emphasizes is just how significantly large, not in statistical significance, but in size of effect, the Hubble tension is relative to all of these other changes in, like, beyond lambda CDM-ness, that they're all smaller tweaks than what the Hubble tension would need. And I mean, this just rams home that the Hubble tension's now been around for more than 10 years, and there's no compelling model solution to it, because it is quite big, I guess, compared to the precision of the data. It's still only like 5%, but it's yeah.
And then here in this slide we are highlighting, we also have this inverse ladder from cosmographic expansion, which is like a model agnostic measurement of H naught, in which it's basically a Taylor series of the scale factor, and that allows us to measure H naught when we calibrate using a prior on the Sun Horizon scale, in this case from CMB. And that measurement as well is not it's in tension with measurement from shoes.
Yeah, I guess just very briefly, yeah, another buzzy thing in cosmology since the DESI results have come out is people looking at what that has to say about neutrino mass. So we did look at that as well, and the sort of notable thing here is that, you know, the CMB constrains is sensitive to matter density in terms of, like, mainly cold dark matter and baryons. Neutrinos are relativistic at that early time. And then when you constrain omega matter at late times with expansion history probes, that's including neutrinos, which are now contributing to the expansion history like matter instead of radiation. So when you free neutrino mass, constraints from the CMB have this degeneracy between the sum of neutrino masses and omega matter that you can see in this gray contour here. And then when you combine with either BAO or supernova, they're able to break that degeneracy by constraining omega matter. And the impact on the upper bound or bounds on neutrino mass can also just be interpreted in terms of what these different data sets want for omega matter. So the fact that BAO wants a slightly lower omega matter than CMB, which means when you combine them, it tightens the upper bound on neutrino mass. The fact that the supernova want a higher omega matter means that blue contour gets kind of pulled upwards in neutrino mass. And it happens to be the case when we combine everything together, you get something pretty similar to the CMB alone.
Yeah, I mean, this feels like it's, again, an indication that this is not the correct model, because when you combine two data sets and you now start widening error bars, that's a very suspicious thing. Because the blue data points are saying that they're more consistent with an area that the gray data points were saying they weren't consistent with, but you've added data. That's definitely a very red flaggy thing for this being the correct model.
Yeah, and I will say in terms of tension metrics, freeing neutrino mass doesn't like qualitatively change things from what tensions between data sets look like in lambda CDM.
And I suppose if you did this in the W0 WA plus new CDM model, that it would just, everything would be very wide.
Yeah, we don't have it in this paper, but just from past analyses, I think if you free W0 WA and then look at what BAO supernova plus CMB can tell you about neutrino mass, the bounds like about like double or something to that order. It just, yeah.
For me, at least, this part of the story is quite compelling for me when you're looking at the DESI results, because they managed to get a very tight upper bound on some of neutrino masses when combined with CMB. That is so tight that one's starting to think that there's a tension between cosmology and particle physics. But then in the W0 WA model, it blows up again, and there's no tension with particle physics. So
a lot of that is, and we sort of see this here as well, though to a less extreme degree, it's a reflection of the fact that in lambda CDM, like especially when focusing on this omega matter direction, everything's a bit in tension, and that manifests in this pull towards very small neutrino mass bounds.
So whether it's W0 or whether it's W0 WA that is the true model or something else, whatever it is, one shouldn't trust the lambda CDM upper bound on some of neutrino masses from cosmology anymore. Cool. That's really exciting. Great time to be a cosmologist. Where are we going to go next? I suppose that's kind of it for the dark energy survey, although you do have your cosmic shear final results, and I have seen 3 cross 2-point combinations with BAO that have some interesting things to say. And then I guess we just wait for, will there be a BAO from, is it LSST or Euclid as well, the cosmic shear, sorry, not cosmic shear, photometric galaxy surveys that we can look forward to as well? And what's the future for supernova as well? I guess LSST will have heaps of supernova there as well.
Yeah, so we'll cover all of those 3 things kind of quickly. So yeah, for the future of DES, as I mentioned, we've reported constraints based on these distance expansion history probes, but there's a lot of science activity ongoing for the final DES year 6 survey. And so we expect to put out cosmology constraints from weak lensing and galaxy clustering, so 3x2 measurements later this year. There's also measurements to come using galaxy cluster cosmology. And by being able to look at these sort of structure growth constraints, both in comparison and combination with the expansion history constraints, you can both tighten bounds and get a sense on like, does this strengthen the preference for dynamic dark energy? You can also do some more, the more data you have to throw at things, the more consistency tests you can do to see if, this story of consistency in the dynamic dark energy model holds up. So yeah, we really want to highlight there's more science to come from DES year 6. And then we'll shift to talk future of BAO and future of supernova, looking at other future measurements.
So I think what we've learned is that, well, BAO is very exciting. I think, of course, we've done this with photometric clustering, but well, I'm going to be talking about the future in general, that BAO science will keep doing a lot to understand dark energy. So we could be looking at higher redshift, where it's closer to when dark energy we believe to start to appear. So what is happening on the spectroscopic side soon is well, very exciting, because we are already in the stage 4 era. So there's Euclid got its first data, and then of course dark energy DESI, the dark energy spectroscopic instrument, already released its results from the first 3 years. So there will be a lot of new results from that on the coming years. And we are already thinking ahead on the next decade. So that's very exciting that, these 2 surveys won't be the end. So people are already planning to build these other instruments that are called stage 5 experiments, from this SPEC-S5 led by the US, this WST in Europe, or this MAST survey in China. So I think all of these will continue to give even more precise measurement of BAO and hopefully understanding dark energy.
And on the supernova side, I think there is also a lot that will happen in the next 5 to 10 years. And here I highlighted some of the main supernova surveys that will provide more data in many different ranges of the redshifts that we're already looking into. So first, probably the first results that are going to come out are from these low redshift supernova surveys, ZTF and Atlas, that are going to improve the constraints on the lower, kind of more recent part of the expansion history. And those are going to increase by at least an order of magnitude and more the number of low redshift supernovae we're relying on. Then, of course, we have LSSD that is gonna kind of do what DES did, just on a much larger area and a much deeper level. So this is going to be very interesting for BAO measurements, but also, of course, for supernova measurements, and will provide probably 2 orders of magnitude more supernovae than what we have been dealing with this. And finally, well, thanks to space telescopes like the Roman Space Telescope, we will be able to really push supernova cosmology to redshifts that has been never explored. Because Roman, thanks to this, thanks to the fact that it's a space telescope, is going to observe roughly 10,000 supernovae 1A between redshift 0.3 but up to redshift 3, which is something that really not even HSD have been able to explore. So in this sense, we're going to have a much wider range and much better constraints on the expansion history of the universe from supernova 1A in the next 10 years.
This ZTF Atlas stuff, what is the time frame for that?
That's a very good question. I think so. Different from Rubin and Roman, which haven't even started taking data, ZTF and Atlas have been taking data for 5 years. And they're both quite close to cosmology. When I say close, it means 1 year, 1 year and a half, maybe a couple. The kind of the ideal timeline is to have these samples ready for when the first LSST Rubin data will start to come out. So that we don't need to combine a stage 4 high redshift supernova experiment with the low redshift samples that are 10 years old that we have been using for the past supernova cosmological analysis. So there has been a lot of push in trying to get these low redshift samples out.
Great. So before we wrap up, what work being done in cosmology do you think is particularly interesting but underappreciated by the community?
Yeah, I don't know if necessarily underappreciated, but just to highlight within the broader field, within these DES analyses, we can gain a lot by really probing results and cosmology constraints using a bunch of different complementary measurements. So the more different measurements show us the results, the more we can understand what happens when we leave out some data, look at other data, the more we're able to build up belief in that what we're seeing is real, or if it is systematics, kind of zoom in on like what kind of systematics or what regions where that could still be allowed.
I like to liken cosmology to kind of a detective story, because it is very observational, right? Like you can't do the experiment and just say, okay, we need to test effect Y. Let's just build an experiment to test the effect Y. You have to look at the evidence the universe has given us and then try and tease it out. So you're right that having multiple different probes that are looking at the same detective mystery but from different angles helps to tease out exactly what's going on.
So to answer the question of what happens when we use the new calibrated DS supernova using Dobeki, here in this plot I show basically the orange contours is what we had before, the DS BAO plus supernovae, GR5 supernovae plus CMB in a W0 WA plane, and then the blue one is what happened when we use this new DS supernova Dobeki.
And you can see that the blue contour moves closer to the CDM, to W0 equals -1, W equals 0 when using this supernova Dove key. And actually, if we measure the tension with lambda CDM using supernova Dove key, this decreases from something that was around 3 sigma to something that's about 2.5 sigma. And a little bit of the reason for this, the decrease in the number of sigma, is related to the values of omega matter preferred by each of the supernova datasets when we interpret them under lambda CDM. So GR5 supernovae prefers a value that it's a little bit larger. You can see here in this plot the blue contour, and then the orange one is when we use supernova Dove key, which is has a smaller omega matter, and it gets also closer to the CMB, as you can see. And the basically, when this effect of decreasing omega matter is also present when we interpret the data under W0 WA CDM, because we see an effect in a W0 WA plane, well, W0 WA plus omega matter space, in which omega matter is going to move to lower values, as in lambda CDM, and also W0 WA are going to move about half a sigma closer to lambda CDM, which is why.
Thanks everyone. If you enjoyed that video, give it a like to let YouTube know you want more stuff like this in the universe. If you have a question or idea, leave a comment, and feel free to share this video with friends and colleagues, and perhaps even check out a video about the supernova data that's flashing on the screen right now. Other than that, thanks Jesse, Juan, Maria, and Santi for the great talk.
Thank you for having us here.
Thank you.